I will be describing problem 6-97, which is a cart with frictionless wheels in a large tank shoots water at a deflector plate, turning it by angle theta as sketched. The cart tries to move left, but a cable prevents it from getting to the exit deflector. It gives us a bunch of terms to use to determine an expression for the tension T in the cable in the term of the given variables. So what we do know is the forces term in the x direction is equal to the forces of pressure, gravity, viscous, and others in the x direction, summation, which is equal to the outstream minus the instream, with the out momentum minus the in momentum. My apologies. So we want to find the T tension of the cable, which is T cable in my notation. But we can assume that pressure is atmospheric everywhere because it's an open cart to the air. So the force term in the x direction for pressure equals 0. There's no gravity in the x direction, so the force term of gravity in the x direction is equal to 0. There's no viscous forces either, so that force term is equal to 0. There's no friction force in the other term of forces, and there's also no inlet term for momentum in this equation because it's a stationary cart. So the solution is that we take our equation and we can simplify it down to just be the tension of the cable is equal to the outlet momentum term, which is momentum flux correction term jet times mass flow rate times U2. And then we can even simplify that out further, or we can expand the U2 out to give us we can expand the U2 term out and the mass flow rate term out to add into the variables that were given. And we can combine those variables to get a much more simplified version of the equation, which is T cables is equal to density times the momentum flux correction of the jet times the velocity of the jet squared times the area of the jet and the cosine of theta. And that will be the expression we can use to find the tension in the cable.